This video is going to talk through the beginning of the 1-2 notes. This section is pretty lengthy, so I'm actually going to divide these notes up into a couple of different sections. So this is going to be our opener. First up, this is a concept review of parent functions, and this may not be something that you've seen very much before, so I wanted to make sure I went over this. We have three different tables here that go with equations. We have linear, we have quadratic, and then we have absolute value. So you can see the equations up above. And I've given these tables because in this section there are many times where you're going to be graphing an equation that has been transformed in some way, and it's always a good idea to be able to graph the parent function, which is what I have written in green. So the parent function is going to be the simplest form of the equation, and then when we transform it, we're going to be transforming the parent into the new function. So these tables are helpful to have. It may be a good idea to copy them down. We will definitely be using the middle table, the quadratic one, in example 1A and 1B. So this is 1-2, transformations of functions. We are not going to be doing the explore and reason for this section. It is on page 13 in your textbook. However, it's not something that I think is going to be that beneficial at this time, so we're gonna skip over that and move on to the essential question. What are the differences between the equation of a function and the equation of its parent function tell you about the differences in the graphs of the two functions? So we're going to be looking at equations, looking at graphs, and figuring out what the differences are between an equation and a parent. Our first example asks us to graph the function f of x equals x squared, which, by the way, is the parent function for a quadratic, like we had on the opening page, for the domain -2 to 2. It also tells us the graph of g is obtained from this graph of f with a transformation of 3 units down, and then we need to say how the equations, domains, and ranges of f and g are related. So the first thing I'm going to do is graph the parent function f. Now it does tell us the domain, which is -2 to 2. So rather than putting arrows on the end of my graph, I'm actually going to put dots. Typically, the domain for this parent quadratic function is -∞ to infinity, but this one is looking at a much more narrow section, just so you can see the movement and see how the equations are related. So I'm using that table from the opening slide. -2 matched with 4, -1 matches with 1, 0 with 0, 1 with 1, 2 with 4. And then I'm going to connect those. And that is the graph of f. Then I'm going to write what I know about f. The domain of f, as given in the problem, is -2 to 2. And it is equal at -2 and 2, so I'm going to be using those brackets instead of parentheses. The range, which would be the bottom to the top of f, the lowest y value we go is 0, and the highest that we go is 4. So the range there would be from 0 to 4. And then the equation for f of x, again, as given in the original problem, is f of x equals x squared. Now I'm going to look at the graph of g. And it says g is obtained from f with a transformation of 3 units down. So to figure out how my g graph is going to look, I'm going to look at these 5 points that I have in f. I'm going to take each of them and move them down 3. So this point, -2, 4, is going to move down 3. 1, 2, 3, to -2, 1. The point -1, 1 is going to move down 3 to 1, 2, 3, -1, -2. 0, 0 is going to move down 1, 2, 3 to 0, -3. 1, 1 is going to move down 1, 2, 3 to 1, -2, and 2, 4 is going to move down 3, 1, 2, 3 to 2, 1. So I'll connect those and label that one G. Now I have to write everything that I know about G. So the domain of G was my left to my right x value. The furthest left that I go on the x-axis is -2, and the furthest to the right that I go is +2. And if you'll notice, the domain of G is actually the same as the domain of f, because I didn't move my graph left or right. All I did was shift it down. So it makes sense that the domain is the same because it's within the same width as the original. The range, though, does change. Now the lowest I go down to is -3. And the highest that I go up to is a +1. The range is still 4 apart because from -3 to 1 is a distance of 4, but it is 3 less on each endpoint than it was from the endpoints of F. Now I have to think about the equation. We kept the same x values, but every y that I got back was 3 less than the y's of F. So to find the equation of G, I'm going to take the equation of F, which was x squared, and I'm going to subtract 3 from that. So it's x squared minus 3. It's the same thing as saying that to get the function of G, we're taking the function values that we get for F, and we are subtracting 3 from those. Same exact thing. For the next example, first we have a definition. Sorry about that. Translation, which is the type of transformation that we just performed. That's where you shift your graph. You're not changing the direction that it's opening or how wide or how narrow your graph is, but you're just shifting all those points some distance and some direction. And each point would be shifted the same way. So you have this star here. If g of x is equal to f of x plus k, then your graph is a vertical translation. Vertical because it's moving up or moving down. If k was a positive number, we'd be moving up, but since it was a negative number, we just moved down.